Hi everyone, so in this last video about organic chemistry, I want to talk about the concept of isomer. So isomers are molecules. They could be organic molecules, could be other molecules, but in this case we're going to talk about organic molecules that have the same molecular formula, but then different three-dimensional structures. So there's two different types of isomers that you can have. We're going to have something called structural isomers, which is basically molecules that have the same formula. The chemical formula will be the same as you'll see in some of the examples later on, but the Lewis structure of these molecules would be quite different. In other words, you'll see a difference in the way the atoms connect in the two different isomers. We also have a slightly more complex form of isomerism, which is called stereoisomer. In that case, the connectivity of the various atoms look the same in two dimension, but when you build a model of those molecules, those isomers, you find that they have a different three-dimensional arrangement. In Chem 11, we're only going to talk about structural isomers. When you get to organic chemistry, then you're going to talk about stereoisomers in detail. So let me show you a quick example of a structural isomer. Here's a formula C4H10, and if I have to draw the Lewis structure of this molecule, there's a couple of different ways I can draw it. One way is if it's just to connect all the carbons in a linear chain that looks like this, okay? Another way, as you can imagine, is if I were to connect three of those carbons together and then put the fourth one as coming off from a branch from the middle carbon, okay? Now, these two molecules, as you can see, have exactly the same formula, which is C4H10. But clearly the way the atoms connect to each other is different. You have the linear connection, 1, 2, 3, 4 carbons connected together, or you have the 1, 2, 3 connections and then the fourth one coming from the second carbon. This is what we call structural isomers. The reasons they're important is because these two are literally different molecules. They have different melting points, they have different boiling points, and a lot of times they have different reactivities as well when reacted with other species. And that's really the reason why we care about them. So to some extent, with structural isomers, you want to think about it analogously to two people with the same name. For example, you might have two people named Ted, but then look very different because they're not the same people. So that's really how structural isomers are. So in this case, we would call this molecule isomer 1 or isomer A and this one isomer B. One of the questions that people always ask is, are isomers the same as resonance structures? And they are not, okay? Isomers differ with each other because the bonding pattern of the atoms are actually changed. So in other words, you're moving an atom or a nucleus to another location in completely different pattern of bonding. In resonance structures, the only things that change are the location of the electrons. So the atoms are all connected the same way. The electrons are moving from one atom to another. So they're completely different concepts. Here's another example of an isomer. We have a formula C2H6O. And when you draw out a structure of C2H6O that satisfies the octet rule, you'll find that you can draw it two different ways. You can draw a molecule that is an alcohol because it has the hydroxyl group right here, and then you can draw a molecule that is an ether. So in other words, ethers and alcohols are isomers of each other, okay? And clearly the function of this molecule is very different than the function of that molecule. Their reactivities are very different. So at this point in Chem 11, we really just want you guys to be able to appreciate the idea of isomers and, to come up with different drawings of isomers given a formula. So an example would be something like this. So here is a question where it says, draw all the structural isomers of this formula, C2H5ON, and then rank the boiling points of these isomers from the lowest to the highest. One of the things you want to do when you are asked to draw an isomer, at least in this class, is to look at the formula itself and try to narrow down the choices that you can have. Given the fact that this molecule has carbon, oxygen, and nitrogen, it really sort of limits you to the functional group you can have, right? So if you think back to all the functional groups we talked about in this class, there's only one functional group where both oxygen, nitrogen are present along with carbon, and that functional group is the amide functional group. That amide functional group looks like this. So then if I start with that as my molecule, then what I need to do with the rest of it is just to fill in the other atoms that I haven't drawn out yet. So in this case would be the one carbon that's left and then the several hydrogens that's left. And I would try to fill it into these backbone of the amide backbone. So here are a couple of different structures I can come up with. So you can see clearly in this case that they have different connectivity. In this case, the carbon methyl group here is connected to the carbonyl group. But here, that same carbon methyl group is now moved and is connected instead to the nitrogen. So clearly there's two different connection happening between isomer A and isomer B. Okay. Now what happens if you come up with a third drawing that looks like the following? So you draw this new molecule here, and it looks like the methyl group now it's connected to the nitrogen, but on this side instead of on that side. Okay. So that is actually not an isomer. Right? Why is it not an isomer of this one? Well, because it's basically the same pattern of connectivity. If you think about it, the N is still connected to the carbon, and then the 3 hydrogens is connected to that carbon. So in other words, we haven't really changed anything here between this drawing and that drawing. The only thing we did is, in a two-dimensional perspective, just flip those bonds. But remember, these are single bonds. Single bonds are freely rotatable around the nucleus, so then you can rotate those bonds easily, and as a result would look like this in one rotation, would look like that in another rotation. On the other hand, trying to convert this molecule to that molecule cannot be accomplished just by rotation. You actually have to break a bond and reform the bond. So that's why these two are isomers. So now that we've figured out that this is not a real isomer, we basically have these two isomers, and then the next question we have to answer is, what is the ranking of their boiling points? Now remember that when we talk about boiling points before, we say that the boiling point of substances are related to the strength of the intermolecular forces that exist in those substances. So in other words, what we need to think about here is which of these two species has a stronger intermolecular force. And that's the one that's going to have a higher boiling point. If you look at both of the molecules, we see that they have a dipole-dipole potential here because there's a carbonyl group, but both of them have that. So that sort of cancels out when you compare the strength of intermolecular forces. The next thing you look at is that methyl group. Well, that methyl group exists in both cases, and that's going to contribute weakly because it's a nonpolar group, so it's going to be a London forces. The one that really distinguishes between these two molecules is the NH bond here. Remember that N is one of those atoms that could form hydrogen bond when it's covalently bonded to another hydrogen. So here I notice that this particular molecule has two H bonded to N, which means there's two hydrogen bonding groups that are possible, whereas in this one there's only one hydrogen bonding group that's possible because this N is bonded to the carbon. As a result, I would conclude that this one has a slightly stronger intermolecular force present, and as a result, it would be the one with the higher boiling point. So that conclusion is written here. So that's really the extent of what I expect you to be able to do in this class, is to draw these structural isomers and to be able to compare the strength of their intermolecular forces to make predictions about melting points, boiling points, and other properties.